All right, so this will be one of the follow-up videos to the CNC versus hand porting video I just made. So again, these are simply my opinions and the way I do business, not to demean or dispute or argue with years and years and years of cylinder head porting technology that's developed and come along. I will first say that I don't subscribe to a lot of the general historical wisdom on cylinder head porting. Kind of do my own thing, and a lot of it defies what the pros say. It just happens to work for me. So, and I've built a program around it. I don't think my program will probably work for other stuff. That's why when people contact me about my products, I try and stick with my products because they're done my way as a simple unit. So, in this, I want to talk about basically lift curve and flow, laminar flow versus port crash and the importance of each or lack thereof. Static flow versus dynamic versus the depression at which you flow cylinder heads up. So conventional wisdom says that this flow bench is outdated and totally useless. This is like from 1977 or 80 or something. It's a SF Superflow 110. The industry standard right now is 28 inches of depression, which takes an SF600 or a 1050. 1050 seems to be about the best thing going out there. The SF600 is right behind it. 28 inches of depression basically came from Smokey Yunick back in the late 60s, saying that at 28 inches of depression, every CFM was worth 1 horsepower. So that just kind of became the industry standard. The problem with that standard is simply that maybe it's true. However, an engine is a dynamic running machine. It doesn't have constant flow. So it's not seeing 28 inches of depression at any given moment. You know, there's a lot of factors going into that. What is important with airflow and using a flow bench is being able to maintain the rates of flow that you find and being able to show differences. Just remember that every flow bench, though, is just like a dyno. It's particular to that setup and that person, how they run it. Unfortunately, since I, work out of my home garage and it's like 88 degrees today, my numbers are going to be skewed. But I've taken the time, kind of a data junkie. I write down, my temps and my corrections and, all that stuff. So I know what I'm looking for on target. Now, the reason I bring this stuff up is because if you look at my flow bench, basically, it won't create 28 inches of vacuum, no matter what. I can kind of get 15 inches out of an exhaust port at a certain point, but most of my intakes end up down around the 5-inch mark, and then I have to do math. I will say what this bench allows me to do is it tells me unequivocally when the port has gotten too big. So if I'm still maintaining airflow gains on this bench at, let's say, 5 inches, I know that I haven't oversized my intake port. And when I say oversize my intake port, I'm talking, these dimensions here. How much cross section I've put into it and all that other stuff. If I go too big with that, I basically lose my top end flow. It just simply won't push any more air because no more air is going to get past the intake valve. When I say that, basically we have a very small window in which to get air completely out of a intake port or exhaust port, whatever. So that right there is basically roughly 650 thousandths lift. All the cams that we run are no more than 630 lift, 635 for the most part. I have some larger things that we do on different stuff. So with that being said, I have to maximize how the air is being utilized to get past the valve, which leads me into lift curve and flow numbers. Now, you'll see a lot of people publish their 6, 7, 800 lift flow numbers. I hate to say it, not that impressive, really, for the most part. However, what I'm looking at when I analyze somebody else's head is the 2, 3, 4, and 5 numbers. So we know that for sure, without a doubt, hardly anybody's going to get over, 640s, 650s, maybe even 670s lifts, especially on an LT car. What that's telling me at that point is that what happens before that is what's critical. And how we maximize that flow is even more critical. Now you hear guys talk about a laminar port. You know, the port needs to flow to 800 lift so it prevents intake crash or port stall. I don't disagree. So my logic behind that is simply that there have been camshafts forever that had much more lift than what a stock head will flow. So I try and keep copious notes and data and things like that. So I'd have to fish through here to find it. But basically the stock LT1 port crashes basically about 525 lift. And at that point, nobody's ever made a 525 lift cam. Even the stock cam is in the 550 lift. So wouldn't you think that GM, everybody else, anybody who designs cams would stop lift at that if the port crashes at that? If laminar airflow was all that important? I don't know. I'm not a smart man. However, what it does do is it holds the valve open during that time frame. Now that kind of leads us back to static versus dynamic port flow like we were talking about earlier. If I sit here and open the valve on the bench to a static position, yes, eventually at a certain lift and a certain flow volume, the port will crash. It'll stop flowing air. What's important though is if I sit here, and I've done it 1,000 times with just the speed of my hand, if I pop the valve open and shut it, the bench never stalls. And that's basically what's happening in your cylinder head. You got to think that intake valve, you know, is going thousands of RPMs a second, opening and closing. The other thing we have to consider is that air is stacked up behind the valve ready to go in as the valve is being opened and closed. So port crash, in my mind, really isn't all that important. I haven't seen it pan out in a car, you know, on the track where it really made any bit of difference, to tell you the truth. However, having more flow up in those areas can be beneficial, as you have to take your lift curve as a whole. So saying from, you know, 0.050 lift to whatever your max lift is, let's say 630, 670, whatever. We have to take that as an accumulative of how much air is getting into the intake system, or into the cylinder, I should say. So once we figure that out, we have to look at where we need the airflow and why. So I'll get into this page in a second. That was an interesting test. Now, just because I use this for port development doesn't mean that's what I limit myself to. I have access to an SF600. Not once ever have I developed a port on this bench that didn't gain quite a bit of flow on the SF600 at 28 inches of depression. The reason being is now that we're force feeding the cylinder, or the intake port, we're forcing air in and around the valve at that depression because the airspeed is much greater. The only thing you kind of have to be careful with on this bench or any low flow bench is how you shape your short turn. So that's a good segue kind of back into lift curve. So when we talk about where's important airflow, we're trying to achieve over 100% volumetric efficiency in a naturally aspirated motor. What that means is that we're actually exceeding the port's volume to flow air. And the way we do that is with valve overlap. Now, valve overlap is the time where both the intake and the exhaust valve are open into your cylinder. So at that point in time, what we're trying to do is have a bunch of exhaust velocity still leaving while the intake port opens. Now we've added vacuum to air coming in from the intake manifold. If you guys remember in the last video, if you watched it, I talked about all the air being, being sucked in. It's not being forced in a naturally aspirated motor. So this becomes critically important of how well does the exhaust valve flow in your 1 to 3 to 400 range. The reason I say that is because depending on the duration, your valve overlap, and where it happens, that will determine on how far to being closed the exhaust valve is when your intake valve actually opens. So I try and focus on that, 300 and lower area, Conventional wisdom says that there's like a backflow problem. You want to limit low lift. I have not seen that happen or pan out on the track or the dyno ever. So what I'm trying to do is maximize that low lift exhaust flow. Twofold. One, on our exhaust stroke, so we've gone through compression, intake, and exhaust valve are closed. Compression, bang, sends the piston down, motivates the motor. Now the exhaust valve starts to open. When that exhaust valve opens, the exhaust is leaving at supersonic speed, so over 2,200 feet per second, which means that's the pop that you hear when it comes out of the exhaust. That's exhaust noise. That's the crack. It's breaking the sonic boom, or the sonic sound barrier, I should say, when that opens. So the more that we can get out at that point before the piston has had time to generate piston speed to push the rest of the exhaust out, the better off we are. So the more we get out as soon as that valve opens, the better. That's all about that low lift flow. So as it does come to max lift, which again is, in the 630 range, which puts us somewhere right in that dimension right there. Think about how little that port is and, well, the area around that valve. And you got to think too, you've got a cylinder right here, that's blocking the rest of this. So the trace line on these heads, this is a stock LT gasket right here. I'll get it positioned properly. That's the cylinder space. That's it. That's all that combustion chamber has to work with. So that all has to be out by then. Now, again, like I said, with cam overlap, as this valve starts to shut, we now have piston speed coming up and pushing the air out, which is great. Because really there's no more momentum. The explosion has happened. So now we're just relying on the piston. But like I said, overlap event happens, exhaust valve starts to close, intake valve starts to open. The air in here is stagnant. It's not going anywhere. It's being pushed against the back of the intake valve, waiting for the intake valve to open. The reason I say pushed is because it's being pulled by subsequent cylinders through your intake manifold to your intake port, and it's just a column of air waiting to sit there to go into your intake port. Now, remember, if you will remember in the earlier video, I said how heavy and hard to move air it really is. Now, there's again no real momentum, especially during the overlap, because the piston is still traveling up towards top dead center. It hasn't reversed direction yet to come back down. That's why this valve, if you have proper overlap, opens some degrees before top dead center, BTDC. If you look at a cam card, it'll be laid out of how the things work. If you get confused, and I do this sometimes, I actually get on my degree wheel. I'll put new cam specs and dimensions and all that stuff on my degree wheel, and I'll just play rotation in my mind so I can visually see it. Now I'm being able to change the data where I want events to happen as the combustion cycle happens. Like I said, I'm not a smart guy. Now, this cross section, as the valve is being pushed this way, you do have a propensity for backflow. However, again, like I said, with the other cylinders pushing, it's pushing pressure just a little bit, not much, on the back of here, helping this come through. But our main effort is, since the air is already being forced this way, it's going to want to continue to go that way. So as soon as this shuts, the piston is now traveling down. We've created force starting this column of air. You can think of a column of air like a slinky. So it's not like the whole column of air moves at one time. It actually expands and then contracts. That'll kind of get into a subsequent video when we talk about port volume versus RPM versus engine size. Seems to be a lot of talk these days about smaller is better and velocity and blah, blah, blah. I'll address that in a subsequent video. However, so as we're going, this valve starts to open, pulling the rest of the air in. Again, that's about all you're going to get lift-wise. So the more we can do to utilize the complete dimension of this valve for proper airflow, the better off we're going to be. So what we want to do is make sure we're using all of the circumference of the valve. That gives us the most actual space to bring air into the intake port. That leads us into valve angles and things that we do to the valves themselves, but I'll cover that in another video. So just quick recap. We talked about combustion cycle, how it works, overlap, talked about flow benches, differences between flow benches, depression 28 inches versus 16 to 5 inches. There's also a new standard for testing your short turn, which is like 44 inches. That's good and all. I would use that. You normally, if I'm developing a blower head, something that's going to have air forced on it, then I'll crank the bench up to 44 inches to see how the short turn works. But that's a whole nother conversation for another time. All right, I'll see you guys.